the improved version of this LSTM cell. Okay, so okay, in Keras, okay, there's no support for the peepholes, but there's an experimental tf.keras.experimental.peephole LSTM cell, okay, which support this idea. Okay, so if you want to use this one, okay, you can call this thing, okay, to create like a peephole LSTM cell inside the keras.layers.rnn. Okay, the way to use it is just like the layer normalization example. Okay. So there are also other variants of the LSTM cell. So, but the only one that we are going to introduce is the GRU cell. Okay, GRU cell is like it's already 50. Let's GRU cell. Let me add one word. Okay, GRU cell is a simplified version of LSTM cell. So as I told you guys that LSTM cell is complicated, right? So because it's complicated, okay, some people think like if we can simplify the LSTM cell, okay, we may be able to keep the performance of LSTM cell at the same time, okay, reduce the computation overhead for the LSTM cell. Okay, so that is like the idea, okay, for the GRU cell. Okay, let's talk about this next lecture. Okay, let's take a 10 minutes break first. Well, okay. Yeah. Okay, so let's continue. Okay, so as I said, okay, the first small variation of LSTM cell is this peephole LSTM cell. Okay, the second, which is a larger variation of LSTM cell, is this GRU cell. So what is a GRU cell? You can have a look at this picture. This is the, the inside structure of the LSTM cell. Obviously, okay, this is much simpler than the architecture in the LSTM cell, right? So this one is called a gated recurrent unit, okay, which was proposed by Kyung-Hyun Chu, okay, Kyung-Hyun Chu in his 2014 paper, okay. This paper actually is a very important paper. Why? Because that paper has two major contributions. The first contribution, obviously, is this GRU cell, okay. The second contribution is the encoder-decoder network, okay. This encoder-decoder network, okay, remember like we talked about 4 different like commonly used RNN architecture. The encoder-decoder network is the 4th one, okay, and which is perhaps one of the most important RNN architecture, okay. For example, like we talk about like if you check out like TensorFlow, like Google's TensorFlow example, okay, the translation network is encoder-decoder network, and it performs very well, okay. So all this, okay, including GRU and encoder-decoder network, okay, the idea was proposed in this 2014 paper, okay. So this Kyung-Hyun Chu is a very important, made a very important contribution. And this guy is actually he's in, I believe he's in Seoul National University, but he's in Korea anyway. Okay, he's in Korea, and in one of the top universities in Korea. Okay, so so let's have a closer look at this architecture. Okay, so first, okay, you can see that, okay, there's really, okay, only one state in this GRU cell, okay. Originally, we have 2 states, right? The long-term state and the short-term state, okay. Now, okay, we only have one state, which is H, okay. So this H, okay, is used to keep pretty much a long-term state, okay. And you can see this H, when it comes in, okay, it is, first like, what should I say? Well, if you take a closer look between this architecture, okay, and this one, okay, first, it doesn't really have what should I say, like a forget gate, okay. So we could say that, okay, not only the state vectors are merged into one, okay, a single gate controller controls both the forget gate and the input gate, okay. So it's this one. this one. So basically, like this is like not only you can imagine this gate has two functions. It's a forget gate. It's also served as the input gate, okay? Because this one is just like what we had earlier, okay? We try to extract like the information, okay, from the current input, okay? That should be kept long term, okay? And this one, okay, this one is like we try to just like a forget gate, okay? We try to get rid of some content from this state in vector so that it can store some additional information there. Okay, so because one is to add to get rid of something, one is to add something, right? So this GRU combine these two gates into one. Okay, this is the perhaps the two most important differences. The first one is the C and H are combined. The second one is like the control gate and the forget gate and the input gate are combined. Okay, so whatever should be kept. Okay, at the same place. Okay, you try to do a 1 minus. Okay, so that you try to get rid of the place that should be kept to be used to keep the new information. So it first removes some part from this edge, and then so that it leaves that space to add new content there. Okay, the other part basically are pretty much the same. Okay, pretty much the same. Okay, and this H and Y are now also combined. Okay, because we only have one state information, so that H and Y has to be the same anyway. Okay, so that's so you can treat, as I said, GRU cell as a simplified LSTM cell. Okay, and the formula, the computations used in the GRU cell, okay, is shown here. But really, like this is not too much different from the LSTM cell, which should be very straightforward. One thing that you can imagine is that this GRU cell, okay, it has it contains much fewer less amount of computations. Okay, so that it's it can converge even faster than LSTM based network if you use GRU cell to build a network. Okay, and the inference, okay, if you use a GRU cell based, if you use GRU cell to build a network, the inference will also be faster. Okay, but in terms of accuracy, okay, sometimes LSTM cell will still work better than GRU cell, slightly better. Okay, based on my lab's previous experience. Okay, the GRU cell still, in terms of performance, even though we say they are similar, but the LSTM cell, still performs slightly better than the GRU cell. So if you want to create a RNN network with the best performance, but you do not, sometimes you do not care, okay, to spend a little bit more time in training, then what the cell you should use is the LSTM cell. Okay, but if the speed is a concern, then use the GRU cell. Let me put it this way. Okay. So okay, So LST and the GRU cell are one of the main reasons behind the success of RNN. Yet while they can tackle much longer sequences than simple RNN, they still have a fairly limited short-term memory. Okay, they have a hard time learning long-term patterns in sequences of 100 time steps or more. So if your sequences, is 100 time steps or more, then even LSTM and GRU cells will not help you that much. Okay, for example, the audio samples. Okay, long time series or long sentences. Okay, in that case, okay, you may not the GRU LSTM cell. Okay, would just not be enough. Okay, it can reduce the memory loss problem, but still, like when the sequence is this long, okay, this problem, the memory loss problem, will still come up. Okay, so one way to solve this problem is to shorten the input sequences. Okay, so we could use what we call, we could use 1D dimension convolutional layers. Okay, so we could combine the convolutional layer with the recurrent layer. Okay, so in the CN chapter, we have learned the two-dimensional convolutional layer, right? So basically, it works by sliding several small kernels, okay, across the image to produce a multiple 2D feature maps, right? We talked about this in the previous chapter, right? So we could build also build a one-dimensional convolutional layer. This one-dimensional convolutional layer will slide a kernel, several kernels, across a sequence, okay, producing a one-dimensional feature map per kernel. Okay, and each kernel will learn to detect a short sequence pattern. Okay, of course, it will be restricted to the kernel size. Okay, it can learn no longer it can learn no longer than the kernel size. Okay, the pattern no longer than the kernel size. So if you use 10 kernels, then the layer's output will be composed of 10 one-dimensional sequences. Okay, so you can view the output as a single 10-dimensional sequences. Okay, just put them together. Okay, and then it'll become a 10-dimensional, but it's a sequence of 10 dimensions. Okay, so you can build a neural network composed of a mix of recurrent layer and the 1D convolutional layer. Okay, you can even have a 1D pooling layer. Okay, if you want. So if you use a 1D convolutional layer with a stride of 1 and the same padding, then the output sequence will have the same length as the input sequence. Okay, if you use a valid padding or a stride greater than 1, then the output sequence may be shorter than the input sequence. This is obvious, right? The knowledge you learn from the two-dimensional convolutional layer, of course, can be extended to the one-dimensional convolutional layer. So basically, this shouldn't be too difficult to understand. Okay. So for example, okay, we can build a model, okay, to predict the sequence, okay, just like what we did earlier. Okay. So except it starts with a one-dimensional convolutional layer that downsamples the input sequences by a factor of 2 using a stride of 2. So like here. Okay, so the first layer is a conv1D filter. We have 20 filters. So it will allow us to output a 20-dimension sequence, okay, with a kernel size 4, stride 2, padding is valid, okay, So input shape is none, 1. So it's going to be, well, depending on the input size. Okay, so it's going to output, because straight is 2, so it's going to output shorter sequences. But basically, I mean, because we have 20 filters, so we are going to have 20 one-dimensional sequences. And you can treat them as like a 1 20-dimensional sequence. And you can feed that into the GRU layer. Okay, here we have 20 unit. Okay, to take a 20-dimensional sequence. Okay, and then because we set a return sequence to be true, so the output, every output will become a sequence which can be used for the next layer, which is again a GRU layer of 20 unit. Okay. And so basically we feed this output to 2 GRU-based RNN layers, and then the output will be put to the dense layer, okay, wrapped by the time distributed, just like we did earlier, okay. And then you can, compile this model, okay, set the loss function to be MSE, use added optimizer, okay. Measures to be last time step, MSE, and then, try to fit, this thing. And then, if you train and evaluate this model, you will find that it is the best model so far. So this one actually outperformed, all the models that we have talked about, including we actually talked about quite a few examples previously, right? For example, this one, simple RNN, return sequence to blah, blah, blah. And then we talk about where is it? This one, remember? So we actually have many versions of RNN network that are used to predict the next 10 values, And this one, the one that combined the convolutional layer and GRU-based recurrent layers, is the one that performed the best. Where is it? This one. So when you train a model, nowadays, because by now we have talked about multi-layer perceptron, we have talked about CNN, we have talked about RNN, and it should come to you that you could combine some models together to solve your problem. To be honest, I mean, for example, when we talk about CNN, actually CNN make use of the fully connected layer, just like a multi-layer perceptron, right? And so it should not come as a surprise to you, the RNN, combines some concept from the previous chapter, such as convolutional layer here. So, having said that, the last topic that we are going to talk about is called Wavenet. Wavenet is the you guys know this company, right? DeepMind. If you don't know this company, at least you know AlphaGo, right? AlphaGo, right? So, I mean, there are several companies that are famous in deep learning. Of course, Google will be one of them. Facebook AI Research Lab will be one of them. But to be honest with you, Google and the Facebook, they have their own prior businesses. Okay, it's not like they are famous. Okay, as an AI company from the start. No, there are some other companies such as like for example, NVIDIA, right? We know NVIDIA is very famous. I mean, for deep learning field, but NVIDIA is famous because of the hardware, right? Mostly because of hardware. The only company that is famous, okay, from the start, okay, as an AI company, AI software company, perhaps is the DeepMind, okay, DeepMind, okay, because DeepMind, as we know, like, I mean, because they have a very important contribution in the reinforcement learning, okay. Unfortunately, I don't think we can talk about reinforcement learning in this class, this semester, but if you guys, I mean, have time, I highly recommend it. Like you guys like check out the reinforcement learning chapter in the textbook. Then you will know like how important, how much contribution, how many contributions. I probably should say that DeepMind, okay, made, okay, to the deep reinforcement learning field. Okay, but anyway, okay, DeepMind obviously is not only making contribution to the reinforcement learning. Okay, they also made important contribution here. Okay, on the Wavenet. Okay, so this is the architecture they proposed. Okay, they stacked one-dimensional convolutional layers. Okay, one by one. Okay, double the dilation rate. I told you about dilation rate, right? This dilation rate basically controls how spread apart, like each neuron's input, okay, or perhaps I should say like receptive field, okay, each neuron's receptive field, okay. So this is like used basically like the higher dilation rate, the wider, okay, the neuron can take care of the input, okay, at every layer. So starting from 1, 2, and then like double every layer, okay. So the first convolutional layer gets a glimpse of just 2 time steps at a time, and the next one gets 4 time steps, okay. So the receptive field becomes 4 times step long, and the next one becomes 8 times step, and so on. Okay, so this way, the lower layer learns short-term pattern, and the higher layers will learn the long-term patterns. Okay, so this is the doubling dilation rate. Okay, this policy, okay, allow the network to process extremely large sequences very efficiently. Okay, so it's actually something like this. You can see the first layer. Okay, it deals with like a two like adjacent input, okay, or like a two numbers in the sequence, 2 consecutive numbers in the sequence. The next one deal with like 4, okay. Of course, it doesn't connect directly to the input; it connects to the previous layer. So the next layer deal with like 8 and so on, okay, and then 16 and so on. So this is like how the network architecture looks like. We call this as a Wavenet architecture. Okay. So in their paper, okay, the authors, okay, stacked 10 convolutional layers with dilation rates 1, 2, 4, 8 to 256, and 512. Basically like 2 to the power of 0 to 2 to the power of 9. Okay, 10 convolutional layers. And then they stack another group of 10 identical layers. And then again, another identical group of 10 layers. Okay, so this architecture is, repeated 3 times. Okay, so the author claimed this architecture, okay, it becomes a single stack. Okay, this single stack of 10 convolutional layers with the dilation rates act like a super efficient convolutional layer with a kernel size like 1024. Okay, except it's going to be faster, more powerful, and use significantly lower, fewer number of parameters. And because like, the shorter the kernel size, okay, the small number of the parameters that need to be trained. I think I talked about that earlier, right? So we don't prefer to use like the larger size kernel. We prefer to use like a stack of small size kernel, okay, to replace like one large size kernel. Okay, so this is the exactly same size here. Okay, so which is why they stack 3 such blocks. So they also left padded the input sequences with a number of zeros equal to the dilation rate before every layer. So to preserve the same sequence length throughout the network. Okay, so just adding some zero to make sure that the output will have the same length. Okay, for easy process. Okay, so we could adopt the exactly same concept of the Wavenet to do our sequence prediction. Remember, we need to predict the next 10 numbers. Remember? Okay. So we can use the Wavenet architecture to do that as well. Okay. So you can see here is the example. Okay. Again, it's sequential. Okay. And then we add chaos layer, input shape none 1. So here, okay, it's just an input layer. Okay. And then we stack up. Okay. 1, 2, 4, 8. Okay. So we stack up 4 convolutional layer. Okay. And then we do it 2 times. Okay, for rate in this one times 2. Okay, so we add like Keras layer conv1d filters equal to 20. Kernel size is 2. Padding is causal and activation ReLU. Dilation rate equal to this one. Okay, so we add like one layer of dilation rate 1, one layer of dilation rate 2, one layer of dilation rate 4, one layer of dilation rate 8, and then we repeat. Okay, because this we have time 2 here, so repeat again 1, 2, 4, 8. Okay, so with this loop we add actually 8 layers of 1D convolutional layer. Okay, and after that, okay, we add one more layer. One more convolutional one dimensional convolutional layer, okay, with 10 filters. Kernel size is 1, okay, and then okay, this will be used as output, okay, and we can compile the model and train the model, and this one, okay, actually outperform all the models that we have discussed so far. Okay, and here, I mean, we just discussed like the code, but I think like the code is very easy to understand anyway. Okay, so the last 2 models offer the best performance so far in forecasting time series. Okay, so in the Wavenet paper, the authors achieved the state-of-the-art performance on various audio tasks, okay, including text-to-speech tasks, producing incredible realistic voices across several languages. Okay, they also use the model to generate music, 1 audio sample at a time. Okay, so a lot of this text is very difficult to achieve. Okay, because a single second of audio can contain tens of thousands of time steps. Okay, remember we said if you're familiar with MP3, you know like a sample rate, right? Okay, the MP3 we know it's MP3 is normally it's like 128K, right? Right? Okay, that's not the I probably shouldn't talk about MP3 because a lot of MP3 songs may have copyright issue, okay? So, but anyway, you get the idea, okay? If you have listened to, or is listening to the music using MP3 files, okay, you know a sample rate is normally 128K or even higher, right? So think about that, okay? That sample rate, okay, 128K per second. That's a lot of number per second, right? Okay, so to deal with such a high sample rate, input and output, okay, this is very difficult. Even LSTM and the GRU cannot handle such long sequences. But the Wavenet is able to achieve that. Okay, so this is just to tell you, okay, if the sequence is not particularly long, okay, let me put it this way, within 100 time steps, then you could use LSTM, GRU cells to create RNN network to deal with that, and it normally performs well, okay, not so bad. But if your sequence is so long that it is in thousands or even tens of thousands such a length, then you should try something different. Okay, you should try to combine the idea of one-dimensional convolutional layer into your model. Okay, and it normally will perform better. If it goes to an extreme situation, okay, such as audio sample, then you probably should use only the one-dimensional convolutional layer to create your model, such as Wavenet. Okay, this is just some suggestions for you. So that's pretty much about it. Okay, for chapter 16, we'll talk about on NLP test, but as I already told you guys, we are not going to talk about this chapter. We are going to skip this one and directly talk about the next chapter, which is the autoencoder. Okay, so give me 1 sec. I think I have this slide on uploaded to the EE class already, right? Okay. This chapter actually has a little bit more than 100 slides. Okay. We have today we still have an hour and 10 minutes, and including the next lecture and the next lecture, we have a little bit more than 7 hours. I don't think we can finish this chapter, but okay, this chapter is going to talk about 2 important topics. Okay, one is about autoencoder, the other one is about GAN. Okay, we should be able to finish completely about the autoencoder. For GAN, we can probably start to talk about GAN, but I don't think we can finish the content about the GAN. Okay, but well, I will do what I can. Whatever I can do. Okay, and but I don't want to rush the class. Okay, I don't want to rush the class. Okay, so I will keep my pace, and if I cannot finish this chapter, whatever I have covered, okay, will be will be the content you need to study for the final exam. Okay. Okay. If I cannot finish the GAN, okay, say I only start talking about GAN, probably I will not include GAN in the final exam. Okay, just want you guys to be aware of that. Yes. It's not there? Eh? 他们上传错了，是不是 ？Okay, let me make sure. Okay, I thought like the student, my TA uploaded the slide, but obviously they uploaded the wrong slide. Okay. Anyway, okay, I'll fix that. I'm sorry about that. Okay. Okay. Yeah, I'll get it done like today anyway. Okay. Okay. So what is autoencoder? Okay. Autoencoder are artificial neural networks capable of learning dense representations of the input data. Okay. So it learns the dense representation of the input data. Okay. The dense representation of the input data is called latent representation or codings. Okay. Perhaps the more it depends on which field you are, but I mean these two terms are used like exchangeably. Okay. So without any supervision, this is very important because you could actually even use autoencoder for like unsupervised learning. Okay, I mean even when the training data is unlabeled. Okay, so the codings. Okay, the codings. I mean I'm referring to this dense representation of the input data. Okay, typically have a much lower dimensionality than the input data. Okay, it will make autoencoders very useful for dimensionality reduction, kind of like a compression. It compresses the data, okay, for you. Okay, compress, not exactly in the what should I say? I mean, later you will see example. Okay, you will see example later. Okay, so so I will also talk about what is dimensionality reduction. Okay, later on, especially for visualization purposes. So autoencoders also act as feature detectors. Okay, they can be used as, for unsupervised pre-training of deep neural networks. I mean, we actually talked about that in chapter 11. Okay, but it's just we didn't because at that time we didn't we didn't really talk about autoencoder in chapter 11, obviously. So I can only give you an idea. Autoencoder can be used for that application, but I cannot tell you. Okay, I cannot show you. Okay, how to do that. But now, I mean, it's different. I mean, because we are in the position to talk about autoencoder, so I can give you an example of that. Okay. So lastly, some autoencoders are generative models. What is generative models? Okay, they are capable of randomly generating new data that looks very similar to training data. Okay. For example, okay, you could train autoencoder on picture faces, and it will then be able to generate new faces. Okay, so autoencoder can be used to generate, the data set. I mean, if you want, but keep in mind, okay, the generated images. Okay, I mean, if you use autoencoder to generate images, okay, they are usually fuzzy and not entirely realistic. Okay, so autoencoder can be used to do that, but it doesn't perform that well. Okay, so we are also going to talk about this generated generative model. Okay, how to use autoencoder as a generative model. Okay, because this is very important. I mean, even for like my research, like my lab's research on like on autonomous driving. Okay, we use like this autoencoder to predict the car's trajectory. Okay, so this is like something that's very interesting. So on the other hand, okay, GAN, okay, what is GAN, by the way? Okay, the full name of the GAN, okay, is called the Generative Adversarial Network. Okay, Generative Adversarial Network. You can see the first word is generative, right? So obviously it can be used to generate the data, new data for you. Okay, so the phase generated by generative adversarial network, GAN, okay, are now so convincing. It is hard to believe that people they represent do not exist. Okay, you can judge this by yourself by visiting this one, a website that shows faces generated by recent GAN architecture called Style GAN. Okay, well, I don't think we have time to talk about Style GAN, but if we don't have time to cover that, I mean, I'll give you the slide anyway, so you can check out this yourself. Okay, you can also check out this one. This person does not exist.com, right? This rental does not exist.com. Okay, to see some generated Airbnb bedroom. Okay, so this is again this place does not exist. Okay, it's automatically generated by the GAN. Okay, so GANs are now widely used for super resolution. Okay, such as what is super resolution? Okay, basically it tries to increase the resolution of an image. So if your image is 120 120 like 400 by 600 by 400, sometimes you want to enlarge your image, right? If you try to interpolate the image, okay, it doesn't look good. But we talk about like this a little bit about this task, like in CNN. But nowadays, like this type of task, I mean, if you want to do a better job, you can use it GAN. Okay, so colorization. If your picture does not have color, okay, you can use GAN to color your picture. Powerful image editing. Okay, for example, replacing photo bumpers with realistic background. What is photo bumpers? Okay, sometimes when you take a picture of your friend, okay, you will see a car pass by, you know, so you don't want that car to be in your picture, right? Okay, so if you take a picture and some unexpected object is in the picture, such as some other travelers, or as I said, like some other cars or anything. Okay, those things are called photo bumpers. Okay, so you I mean, a lot of times you want to remove those photo bumpers, right? But of course, not just removing those photo bumpers. You also want, after you remove photo bumper, you want to put the background so that it looks nature, right? So it can, the GAN can also do that for you, okay? And turning a simple sketch into a photorealistic image, predicting the next frames in a video, okay? Augment the data set, basically generate a lot of like pictures to train other models, okay? Or generating other types of data, such as text, audio, and time series, identifying the weaknesses of in other models, and strengthening them, okay, and more. So GAN is a very powerful model, okay. So well, let's talk about this like you know, after a break, okay.